Okay, so section 3.3, properties of functions. Okay, the first thing I want you to know is that in this assignment, we will be using interval notation. We have been already using it a little bit. So let's just review interval notation really fast, in case you're not yet comfortable with it. Interval notation is where you use either a parenthesis or a bracket, and you do your smallest number of an interval. An interval is a group of numbers, right? Like from one number to another number, so it's continuous in between them. And then you do the largest number of the interval, and then you either close it with a parenthesis or a bracket, right? Have we talked about interval notation before? It's kind of a weird way to explain it. Now, if it goes to infinity, we use negative infinity to whatever number we want it to be. So let's pick a number. Negative infinity to 3 would mean that whatever number we're talking about, let's call it x, means that x is less than or equal to 3. Why does that mean that? Okay, equal sign gives us brackets. So maybe we should make a note about that. Bracket if equal, parenthesis if not. Okay, what did someone else say? What does this statement mean? X is less than or equal to 3. What's the largest number that x can be? 3. And then it's less than it. How low does it go? It doesn't say how low it goes. So when it doesn't say, we just assume it goes down to negative infinity. And notice how the number negative infinity is smaller than the number 3. So the negative infinity always goes on the left. What if we were doing a positive infinity? Like what if we wanted x is greater than 6? How would we write that in interval notation? 6 to infinity. Would a positive infinity ever be on the left? No, it's always on the right. It's always the biggest number. Okay, what if we had something like x is between 0 and 10? How do we do that in interval notation?
You do 0 on the left side, 10 on the right side with brackets.
Okay, brackets on both sides?
Oh, no, never mind.
This would be a parenthesis on the left and a bracket on the right because I did no equal to here and yes, an equal to there. If x, okay, this statement means 0 is less than x, so x has to be bigger than 0, and x is less than or equal to 10. The parenthesis tells us that x cannot be 0, but it starts right after that. So x can be 0.1, 0.001, 0.5, 1, 2, 3, 4, 5, 6, all the decimals in between, until it gets up to 10, and it includes 10. But once we get to like 10.1, it no longer fits anymore, right? So it includes 10, so we put the bracket, but it only goes down as close as it can possibly get to 0 without including it, because it's not equal to 0. It is equal to 10. If I hammered that enough? Good. Okay, so that's the first thing you need to be aware of. The next thing we're just going to officially write is that a function can be increasing. So we talked about that. Increasing means that the y value increases as x increases. So as you move right across a graph, your graph is going upward, like that. Decreasing means that the y value decreases as x increases. So as you're moving from left to right so that x is increasing still, the y value, or the graph, is going downward. So we kind of talked about that already on the little graph we looked at earlier. Does that make sense? What would constant mean? We didn't talk about that because there wasn't any. Y stays the same as x increases. I heard someone say horizontal line, which is exactly right. Thought I was writing x-intercept, I think, so I put a dash. Okay, so it'll be a horizontal line that is constant. Will you ever get a vertical line in a function? No, because then it would fail the vertical line test. Okay. Now we have things like absolute maximum and absolute minimum. Do you need me to actually write that down? The highest the graph goes and the lowest the graph goes, because you are going to see that on the assignment. So should I just do like local mins and maxes? Yeah. So a local minimum would be where the graph changes from decreasing to increasing. Or in other words, it's just low points on the graph. So any of those lower little loop-de-loop things are local minimums. Okay? So then local maximums are where the graph does what? Changes from what to what? From increasing, so going up, to decreasing, coming back down. So that ends up giving us high points in the graph. Okay, now we're ready to talk about symmetry. Fortunately, we've already learned symmetry, so this is just learning some new words for the symmetry we've already learned. Are you ready? If you don't want to write this down word for word, or if you just want to write down the words to remind you, or a picture to remind you, and I don't care if you write every little teeny thing down when you're taking notes. Whatever you need to remember. So, done? Are we good? Okay. Symmetry is our last thing. Okay, there are two types of symmetry for functions. We talked about them briefly already. The first type of symmetry is called even symmetry. Even symmetry is when our graph is symmetric to the y-axis. Y-axis. Graph is symmetric to the y-axis. So for example, if I have a parabola that's symmetric to the y-axis, we say that that graph has y-axis, we actually say that this graph has even symmetry. So instead of using the term y-axis, we use the term even. Okay? An official way of saying that is that for every x, f of x is equal to f of negative x. Why is that true? So if we have a point over here at x, we get a certain y value. Because it's symmetric, for that same value at negative x, we're going to get exactly the same y value, like somebody having the same birthday, right? This is the type of symmetry where when we did y-axis symmetry before, you plug in negative x for x, and then you simplify, and what does that tell you? If your equation ends up being the same, if equation is the same as the original, it has even symmetry. The reason it's called even and the reason it ends up having even symmetry is usually that you have even exponents. What do even exponents do to negative x's? Like, for example, if I had like y equals x to the fourth minus x squared, what do those even exponents do to a negative x? Make them positive. So what ends up happening? We get the same equation again, and it has even symmetry. Right? Even symmetry is the same thing as y-axis symmetry, and what happens is if you plug in a negative x and you simplify it, you get the same exact equation back that you started with. Okay. Alright, the next one is called odd symmetry. And odd symmetry is where your graph is symmetric to the origin. So for example, if we have a graph that looks like this, I don't know how well I did. Did I do okay? If it looks exactly the same upside down, then it has odd symmetry. So it's like a 180-degree rotation. If it looks the same upside down, it's odd. Okay? Our technical definition for this is for every x, f of x is equal to negative f of negative x. What the heck does that mean? So if I plug in an x value and I get a y value, then if I plug in the negative of that same x value, I will get the negative of that same y value. That's what that's saying, because remember how f of x means y, right? So if I have a point here at x, y, I'm going to have an identical point here at negative x, negative y. That's what that says. That's what that means. Okay? You know how when we did origins, okay, when we did x-axis symmetry, we would plug in a negative y. Do we even usually have a y in our equations when we're dealing with functions? No, it's an f of x. So we're not going to plug in a negative for y anymore. Remember how when we did origin symmetry, we would do a negative x in for x and a negative y in for y? Instead of doing that, we're just going to put the negative x in for x. And then if that turns the whole problem negative, then it's origin. Because for a negative x, we should also get a negative y. Okay, let's look at an example. So let me explain this. To find origin symmetry, plug in negative x for x. What this means is all you ever have to do is plug in a negative x, and you've just tested it once. Instead, remember how when we did when we did x-axis, y-axis origin, you had to like test it 3 times? You're not going to have to do that with this. You just test it twice. Not test it twice. Test it once. And that once will give you your answer. Okay? All right. If the equation is negative of what it used to be, it is odd. Okay. What if neither of these work out?
None.
We usually just call it neither. It's neither odd nor even. Okay, let's look at an example though, like an equation. If I gave you f of x equals x to the fifth minus 3x to the third plus 1. What happens? Oh, I don't want 1. I would do like plus x. Sorry. That's going to mess it up. That would make it neither. I just want to do plus x. What are the powers on all of these? The powers are all odd. Okay, so if we do a negative x to the fifth minus 3 negative x to the third plus negative x, that turns our equation into negative x to the fifth plus 3x to the third minus x. What happened to all of these signs compared to all of those signs? They're all opposite. Now, is it important that they all be opposite? Yes, it's like you took the entire function and multiplied it by a negative. So every single sign has to change. If one of them if two of them change and one doesn't, which is what would have happened if I left it the way it was, let's write that one down. X to the fifth minus 3x to the third plus 1. If we do that one, we would end up getting a negative here and a positive here, so those would change, but would the last one change? No. Notice how this one's the opposite. This one's the opposite, but this one stays the same. So that one would be neither because it's not everything changed to a negative. Now where this gets complicated is when you do problems with fractions. So those are the ones you're probably going to have questions on. Didn't we do fraction ones when we did x symmetry, y symmetry, and origin symmetry? We did do some fractions then, didn't we? You're not sure. I'm pretty sure we did. You guys are tired, and I'm not sure. I will find a fraction example if you want me to. But if you don't want to listen to me anymore, I'll just let you play around with it and see what you can figure